Welcome back. In this video, we're going to further our techniques of integration by looking at another integration by parts example. In this specific example, we are dealing with some trig. We've got cosine. So we want to solve the integral for e to the x times cosine x integrated with respect to x. Now, we have two pieces here, right? We have, we look at this, we go, all right, well, I don't see the derivative of cosine or the derivative of e to the x hiding in there. Therefore, that lets me know it's probably not a u substitution. So when we think about choosing, we generally use our rule of thumb. We say liate. And when we consider that, we've got logarithmic, inverse trig, algebraic, trig, and exponential. And generally, we would pick trig to be my u since that comes before exponential. But I just want to show you that's not always the case. In this situation, I'm going to let my u equal e to the x. Then v prime will equal cosine x. So if I find the derivative of u prime, that would also equal e to the x. And if I look at v, integrating cosine x, that gives me sine x. And I could likely solve this problem if I had chosen cosine x to be my u value instead of e to the x. But we're going to just see an interesting pattern here, because one thing we know, the derivative and the integral of e to the x is always going to be e to the x. And remember, when we consider the integrals and derivatives of sine of x and cosine x, the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine gives me negative cosine, and taking the derivative again, it would continue to circulate and we would get positive sine. And of course, the integration is exactly the same, but in the opposite direction, right? So we have two functions that are rather, I'll describe them as circular when we do these repeated derivations or integrations. Okay, so let's see what happens here. So remember your integration by parts formula. The integral of uv prime is uv minus the integral of vu prime. So setting that up, I'm going to have that this integral equals u, e to the x, times v, the sine of x, minus the integral of vu prime. So that would be e to the x, that's my u prime, and sine x. Of course, we write our dx at the end. So essentially what we have to do is we need to do that integration by parts again for this second one, right? So this integral that we now have in our first iteration of integration by parts is very, very similar to what we started with. So what we'll notice is this is going to be circular in a sense. It's going to end up repeating itself. So let's look at this. I have that u equals e to the x, which would give me u prime equals e to the x, and then v prime is sine x, so v would be negative cosine x. The integral of sine is negative cosine. So bringing down what I have, I'm just going to pull this down to the next line, e to the x, sine x minus. So my integration by parts, again, is u times v, e to the x, times negative cosine x, minus the integral of vu prime. So that would be negative, let me use my colors, negative cosine x times e to the x. dx. So simplifying this just a little bit, I have e to the x sine x plus e to the x cosine x. Those two negatives turn positive. Negative, negative, that will be positive, but then I still have a negative here, so this would be minus the integral of e to the x cosine x. So this piece is exactly what we started with. And here we have to get creative with how we write our answer. So I'm going to rewrite this line we have here. I'm going to write it with my original integral. So we started with the integral of e to the x cosine x dx. And what we have said is that it's equal to all of this. We did 2 integration by parts to get this line at the top of the screen. So I have e to the x times sine x plus e to the x times cosine x minus the integral of e to the x cosine x dx. And so again, as I said, you'll notice this is exactly the same as what we started with. So what we're going to do here is I'm going to add this integral, negative e to the x cosine x dx. I'm going to add the opposite of it, use some algebra, and move it to the other side of the equation. Now, doing this gives me 2 of those integrals on the left side of my equation. So I just use the, inverse property, or I'm sorry, the addition property of equality to move that to the other side of the equation. So remember, because we were doing integration, we have an arbitrary constant over here on this side. So I'm going to write plus c sub 1. All right, I could call it c if I wanted. It's just we're going to end up with a second c value here. So we're going to kind of write it in a special way. So I've got plus some c value because this integral is equal to those integrations plus an arbitrary constant. So what I can do here is I can divide on both sides by 2. So this tells me the integral of e to the x cosine x dx is going to equal e to the x sine of x plus e to the x cosine x over 2 plus this arbitrary constant divided by 2. So I can rewrite this just to clean it up. I'll say 1/2 e to the x sine x plus e to the x cosine x plus some constant, I'll call it c, but I have to put an addendum on there. Because I did that dividing by 2, we're going to say c, that arbitrary constant, is equal to c sub 1 divided by 2. So whatever arbitrary constant we would have calculated, because I moved that integral aside, I have to say, well, this new arbitrary constant is going to be half of that because I'm dividing by 2. So I hope that makes sense. You don't see that a lot, but it definitely occurs when you're dealing especially with e to the x and your trig functions sine and cosine that are very circular as you integrate and differentiate them. As always, please email me if you have any questions.